One ball rolls to the right at 4 meters per second, has a mass of 400 grams. A second ball rolls to the left at 2 meters per second, has a mass of 200 grams. If the two balls experience a totally elastic collision, what are their final velocities? So I think this time around I'm going to start by sketching here just to make sure I don't screw anything up. I did screw up which pen I had selected there, so let me fix that. Anyways, let's see, 400 grams. This one's to the right? I was going to make sure I get these details correct. So that's 4 meters per second to the right. This one doesn't have as much symmetry as the last one, though, because the last one kind of had sort of equal and opposite momentum, if you will. That's maybe one way of looking at the symmetry. That's why it had 0 center of mass velocity, right? But this one is different because we have the second object is a mere 200 grams and is moving at 2 meters per second, but to the left, so I should draw that in here with a shorter arrow. I don't know if I have enough. Let's see. Let's put it up here. 2 meter per second there. I think maybe that's enough. I'm not going to write all the variables. Maybe that's enough for me to start calculating with these formulas what numbers to put where. Maybe I will put the little label, though, like, hey, this is going to be object number 1. This over here is going to be object number 2. So when I see the subscripts, I kind of know where to look to know what number to put. So doing V1 first, we're looking at M1 minus M2 over M1 plus M2 times V1 naught. So the masses will be 400 minus 200 over the total of 600. That's kind of the same as last time, right? So hopefully still familiar. But that is a clear positive 4 meters per second there. And then we're talking about plus 2m2 over the total mass, so that's going to be 2 times the 200 gram this time divided by 600 gram, and then this one will be multiplied by minus 2 meters per second. Maybe it would have been useful for me to write like V2 naught is equal to minus 2 meters per second, because just looking at a picture, it's still potentially easy for me to overlook that minus sign, but maybe it's good enough. Okay, for now. I didn't screw it up, right? So, but again, word to the wise, be careful about that. Anyway, so we have, I think 400 minus 200, 200 over 600. I think that's a 1/3. Again, 1/3 times 4 meters per second. And maybe this time I'll just go minus, take this minus sign out front. In other words, 2 times 200 is 400 over 600 is 2/3, because we all love fractions, right? Since I already pulled that minus sign out, I'm just going to put 2 meters per second here. Make sure if you do pull that minus sign out, then don't still keep the minus sign here, because that would be another way to screw it up. Minus signs are not really your friends, right? It just lead to lots of pitfalls, I guess. But something we got to learn about in physics, I think. Let's see. We have, oh, look at that. I think it's 0, right? Because this is like 4/3 minus 4/3. So I believe that's equal to 0. Wow, that was simple. Maybe there's some reason for that. Let's look at the second one. It says V2. We're going to use that second formula there. And okay, so that's going to be 2 times 400, I think. Okay, 2 times 400 over, it's always over total mass, so 600 times 4 meters per second. You know, at some point you realize there's a pattern to these, right? And you just got to make sure not to mix up any parts, I guess. But let's see, M2 minus M1 in this case would be 200 minus 400 over 600. I always want to make sure to pay special attention to like these, make sure I put things in correctly, right? Minus 2 meters per second. So again, trying to make sure we have all the minus signs correct there. And let's see what happens. This 800 over 600, I think, is 4/3 again, times 4 meter per second. Here we got 200 minus 400 over 600. That's like minus 1/3 times minus 2. That's maybe the same as like plus. I'm just going to cancel out the signs already. Plus 1/3, excuse me, times 2. Make sure to do that correctly, right? Canceling signs. Okay, so let's see. That means I've got, let's see, 4 times 4 is 16 over 3, right? Plus 2 over 3 is 18 over 3. I think that is equal to 6 meters per second, right? And let's see, does that make sense? I think one way of looking at this, like I always ask, like, does it make sense? Well, we've got a big mass coming in with a lot of speed. It hits this littler mass. Apparently, though, that's moving with less speed. Apparently, though, the collision is enough. Like some momentum is going to be transferred. Basically, I think the mass M1 is transferring all of its momentum to the mass M2, That's why it winds up moving with a final velocity equal to 0. But since the second mass is a lesser mass, if that's a lot of momentum transferred to it, right? So since all of that momentum was transferred, although it did have a little bit going to the left to begin with, but a lot was transferred into it, so it kind of makes sense that maybe it has a really fast rightward moving velocity. You might remember we had a formula earlier that said the difference between the initial velocities and the final velocities should be the same, which you might say, well, let's see, 4 minus 2 is 2, 6 minus 0 is 6. Did we screw up? But wait a minute, it was really 4 and minus 2, and the difference between those two is 6 meters per second, which is the same as the difference between these two. That's a check I often like to do just to make sure I didn't screw things up. So hopefully that means that when we check this, we get the correct answer, and it looks like we did. And in fact, it says here to the right, which aligns with the way we've been interpreting the minus signs for my answers. It does give us a follow-up question here. It says, what is the center of mass velocity? And I think what I'm going to do here is, let me see if I can do this without, sometimes this bugs out on me, but I'm going to try to delete all the stuff. Actually, wait, no, I take it back. Let's not delete all the stuff. Let's keep the picture. We'll just delete this stuff. I was about to delete too much. Okay. Oh, good, it worked. Sometimes this program bugs out and it doesn't recognize properly everything that's inside the circle or rectangle that I drew, or pseudo rectangle. Center of mass velocity, right? So, like, in that sense, let me go over here. Does everyone remember the center of mass velocity formula? I don't have a ton of space, so I'm not going to rewrite it, but I think you do the weighted average, right? So we're going to take like 400 times 4 meters per second, and then it's going to be plus 200 times the minus 2 meters per second, okay, divided by the total mass of 600. And I've left off the grams because I already know they're going to cancel out, and I'm trying to be efficient with my use of space here. Let's see here. Maybe we could like divide off a common factor of 200, right? Because that would leave you with like minus 2 here. This one would still be like a 2 times a 4 would be sitting an 8. 8 minus 2 is 6 over 3. So I'm seeing 2 meters per second as a center of mass velocity. And I think if we check the answer, there it is, that was correct. I want to show you something with this though, because it asked that question, but could we do anything with that? The picture I've drawn here is kind of the picture from really the way this thing was given to us, right? I don't know what else to say. It's maybe a picture from like the Earth frame or the lab frame, you could call it. In other words, it's just as given. But what if I looked at things from the center of mass frame, right? So if I imagine somewhere in between these two, I guess it would probably be closer to the 400 gram object, but let me just put a little point right here, say that's the center of mass. But if these two objects are really moving as reported, then that center of mass point itself is going to have its own motion, right, of 2 meters per second that way. So how would things look from the perspective if I said, you know what, I'm watching this process, but I'm sitting here like writing on something that's moving at the same speed of this center of mass point. Maybe I'm just writing on the center of mass point. Maybe I have to be as small as an ant to do that. I don't know. But I'm going to look at it from that perspective. And from that perspective, like, what would I see? Well, I'm going at 2 meters per second to the right. The 400 gram object is catching up to me at 4 meters per second, but that really means that the 400 gram object is moving towards me at kind of a net, maybe net, I don't know if that's the right word, but net speed, relative speed, actually that's the word, relative speed, I'm a physicist, right? That's the right word, relative speed of 2 meters per second, right? Again, this is as viewed from my viewpoint at the center of mass point, which you could call the center of mass frame. So that's kind of what I'm trying to draw here. And then the 200 gram object, since I'm moving at 2 meters per second towards it, and it's moving at 2 meters per second towards me, the relative velocity that would make sense for that, it's going faster towards me. It's kind of, it's like an analogy to this would be if you're going at 30 miles per hour in a car, and then there's a car that's coming in the opposite direction on the road at 30 miles an hour towards you, how fast are the two of you really moving towards each other? The answer would be 60 miles an hour because you're just summing up the speeds that both of you are going, right? But you're going opposite direction. So hopefully that makes some intuitive sense, because that's where I'm getting this 4 meter per second here for the 200 gram object. That's the center of mass frame. Now we know that in the center of mass frame, this is kind of the initial picture, right? But the final picture would be what we noticed in the last example is, in fact, this I think is the last example we did right here. So really the example we just did is the same example, just looked at from a different point of view. So we already know what happens, right? We know that the 400 gram object is just going to bounce off at 2 meters per second, okay? And the 200 gram object is going to bounce off at 4 meters per second. I probably didn't draw that arrow large enough to reflect that, but oh well. And so that would tell you that in the center of mass frame, here's the way I would write this, is I would say V1 prime is equal to -2 meters per second. V2 prime is equal to 4 meters per second. But then if I want to find out what really are the appropriate final answers, I need to add back the center of mass motion, because I'm viewing this from the perspective of the center of mass point and how it's moving. If I want to know what it's going to look like, say from like the side of the road or something like that, not me moving in my car along the center of mass point, right? I don't know if that's really the situation, but still. But I'd have to add that 2 meters per second. So -2 plus 2 gives me, so that means V1 would be equal to 0. And V2, if I add 2 to the 4, I get 6 meters per second. The same answers I just got using the formula. So I've tried to show you a little bit here in kind of words and pictures, like another process that takes advantage of the very symmetric view that you get in the center of mass frame. This can be, with some practice, you can actually kind of automate this process, or maybe like turn it into an algorithm, like write like a set of like, I don't know if it's 3 or 4 steps. So we could try that, or you could try that on some examples and see if it works. It's an alternative to having these formulas written down. It's also an alternative if you don't happen to have them for whatever reason.